In this video we come back to these batteries that we looked at in the last video. So I missed a lot of stuff on the project and basically started at the results of that project. So let's go over that project. So to begin with, I charged these batteries independently. I kind of went over that in the last video, but battery number 1 here has the most milliamp hours, and that tells us what its capacity is. So for the voltage range that we charged it over, this particular one, we got 781 milliamp hours, so slightly lower. C3, which I have battery 3 in, C3 up there, C4 there, 749 milliamp hours, went down a little bit again. And then C4, we have our lowest capacity battery, 723 milliamp hours. So they all started at the same voltage when we started charging, and they all got charged to 4.2 volts. Now the numbers that are written on there, I didn't know what the capacity of these batteries were, but I had them all at the same voltage. I put them in series, and this one discharged, or its voltage dropped the fastest. That one, the voltage dropped the slowest, and then these were in between. So based on how fast their voltage dropped when they were passing the same current, because they were in series, I could tell that this one had the highest capacity and that had the lowest capacity. So now we charge them to 4.2 volts, but it's important that we don't hold these batteries at 4.2 volts, because as we'll see here, the voltage dropped on the batteries. This one's 4.12, this one's 4.11, and interestingly, this one's 4.18. Earlier is 4.11, so I don't know what happened there. This kicked some current into it or something for some reason. And this one's 4.11. And the batteries, you charge them to 4.2 volts, but they really don't like to stay at that high of a voltage. They naturally drop a little bit. Looks like this is about where it's going to level off, at least for a while. And at about 4.1 volts. And yep, it started charging. So that's the problem. I disconnected it and reconnected it, but they had all discharged to 4.1 volts. So now I was going to show this anyways, but this actually worked out okay. We accidentally charged this one a bit more than the other ones. So what we're going to do is connect them in parallel. So as I said, I was going to talk about this anyways. While they're in parallel, this will hold their voltages equal. So this one's slightly more charged. I think it'll fit a little better here. And this pack is actually made for flat top 18650 batteries, but these will actually fit, really tight fit, you know, because they got the button top. This part sticks out a little bit more. But in any case, we should probably do our highest capacity battery. They are less than 1/10 of a volt difference. This one was 4.12. That one was, I think, 4.18. So less than 1/10 of a volt difference. So current's going to start flowing out of this one into this one until their voltages equalize. But at that low of voltage, it shouldn't be a high current. But in any case, we'll put all 4 of them in here. You would not want to do this when they have a large enough voltage difference. I'm not sure what the exact voltage is. I'll try to find that, but under 1/10 of a volt, I think we're alright just connecting them in parallel. So now let's talk a bit more about the benefits of batteries in parallel. And so, as we said before, the voltage has to be equal while they're in parallel. And so before you put them in parallel, because the one with the highest voltage is going to charge the lower voltage ones until they have an equal voltage, we want to make sure that they're close in voltage to begin with. And we were less than 1/10 of a volt difference. So I felt pretty safe connecting these together. But this one charges the other ones directly when it had the higher voltage, and so it's important that they were close to the same voltage to prevent too high of current from flowing. And so in any case, now they're all equal voltage. And what that means is we have all the positive to this rail, all the negative to this rail. Those 2 rails go to this circuitry, and it takes the current they provide and outputs 5 volts here. We also have an option with this particular pack. There's a 3.3, 5, 6, 9, and 12 volts there, but I think only the 9 volt and the 12 volt worked when I tested it out earlier. So this is just a cheap pack, but it's nice because I can actually plug batteries in even when they're a little bit longer, but because they have the button on top. But in any case, the number 1 we measured had the highest capacity, number 4 had the lowest capacity. So all of these are going to provide current to the circuit here, which will power a load, but since number 1 can provide more current for a given voltage drop, because remember all their voltages are going to stay equal, since it can provide more current for a given voltage change, it's going to provide most of the current, or not most of the current, but more current to the load than the batteries that are lower. So they're all going to be providing current, but the one with the highest capacity is going to be providing the most current because they're all going to change their voltages equally. Whereas 4 cannot provide as much current for a given voltage change, so it's going to provide less of the current. But still, they're all going to provide current, and ultimately what we're doing is kind of making them one battery in a sense. And you're taking the capacity of each individual battery and just adding them together, and that will be the capacity available for the load. So these are about 750 milliamp hours on average, and so you would multiply that by 4. So I think right here we would have about 3,000 milliamp hours provided there. So now there's batteries, single lithium ion batteries with that capacity and even more, and so these are really cheap, but this is nice for a demonstration. First off, they're not storing as much energy, so if something does go wrong, one of them catches fire, the fire is probably not going to be near as big as a higher energy battery. And also, since they're not perfect, they got larger imperfections. Those imperfections are going to show up, and if we can build a circuit to compensate for those imperfections with these crappy batteries, that circuit's going to work even better with better batteries. So now we're going to come to connecting batteries in series, especially lithium ion batteries. So to begin with, let's get a baseline voltage reading of the batteries. They should all be equal since they're parallel, and 4.12 volts. That's what they should all be when we take them out and measure them individually. And so to connect them in series, we're going to use this battery pack, which these straps came with to strap the batteries in, and it gives 4 series batteries and then 2 terminals where we have this barrel plug output. And so we doesn't really matter what order we pop these out, but let's do it in order anyways. And all we have to do is snap it in. So again, negative where the spring is, positive where the little bolt is. And then over here we got negative, which actually over here we have the negative of this side connects directly over to here where we connect the positive side of one battery with the negative going to the spring again. And of course we just keep popping them in. So this is pretty typical way to connect batteries in series like this. Should not be unfamiliar probably to anybody, but the main thing is we take the 4.2 volts of each battery, or 4.12 volts I should say, so about 4.1 volts. So when we measure the output here, we should have 16.4 volts. So now let's actually take a measurement of the voltage. So we got the barrel plug here. I know that positive is in the center there, and the negative is on the outside. Now I said 16.4 volts, should be about 16.48 volts, because these are all about 4.12 volts, and we multiply that by 4. And there you can see we got 16.48 volts. So what this is doing, it's taking the voltage of each battery and adding them up. And then when they're equal voltages, you just multiply them. Pretty simple. So in any case, what we have now is we have increased voltage, of course. And 16 volts isn't something to play around with. If you know about car batteries, you know that if you directly connect two metal pieces that are connected to a car battery, which is about 12-13 volts, that will fuse them together. And so it's not something to play around with. You want to make sure you don't short circuit anything. So I have the barrel plug. I'm going to use barrel plugs to help try to prevent short circuits. And then these battery packs, they have little dividers to separate the metal points of the batteries, because you don't want to directly connect the negative side of one series battery with the positive side of the other. You'll have a current loop there, and that's a short circuit, so that's bad too. So you want to protect against that. Now, for this video though, what we're interested in is how fast the battery's voltage drops. And so they're not widely different in their capacities, but they are different. So number one has the highest capacity, which means for a given amount of current, its voltage is going to drop the slowest. Number 4 has the lowest capacity of these 4 voltages, so since they're in series, its voltage is going to drop the fastest for a given current. And the reason why that is important is because whatever current is flowing at the output here into whatever our load is going to be, that same amount of current is also flowing through each battery because they're in series. There's one current path. And so, well, this one's passing a certain amount of current. They're all passing the same amount of current. The voltage is going to drop slower for this one than the other ones, especially number 4. And so 4 is going to have the fastest voltage drop. And there's a danger when we get to 2.5 volts. That starts doing damage to the battery below 2.5 volts, which will likely cause problems in the future. So you want to make sure your lithium-ion batteries never drop below 2.5 volts. Now, it's going to drop to that voltage at first while it is powering a load. So that's most crucial. You don't want to unplug it and then measure the voltage, because the voltage is going to be lower while it's powering a load. It's going to rise up a little bit. You don't want it 2.5 volts while it's powering a load. So that's main takeaway for now. So now I think I explained everything as well as I should. Probably explained it too many times, but it's important stuff. So I removed those wires to help reduce the chance of short circuit. We're going to apply power to, there you can hear a click, to our low voltage cutoff module, whatever it's called. And so let's try to get the light where it shows up better. There we go. And so right now 16.3 volts, it's measuring the voltage of the batteries. If we hold down this button here, or now it's showing us what it is, but if we hold it down, now we can program the voltage that it will shut off at. It'll shut off the output. And so I want it at 12 volts right now for whatever reason. So let's wait for it to stop flashing. So right now it's 16.04. If it goes down to 12 volts, it will shut off. Now let's press that button. I got 3 volts set there. So let's hold down the button. Now the 3 volts flashes. We can raise that or lower it. So this is how many volts above our shut off. So it's going to shut off at 12. But if it goes up 3 volts to 15, it will turn back on, as we see now. And one thing I noticed before was, even if I hadn't got a high enough voltage for it to turn back on, as long as it was above the shut-off voltage, if I unplugged it and then replugged it in, it would the output would turn back on. Our load is going to be 4 series resistors. So again, we will change the light to kind of get a better view of the leads here. You can see that one's in the positive rail. It comes, and basically I connect them where they all connect together until we get to the negative rail. So we have a current path from positive and negative through there. We can take the jumpers here, and I disconnected the batteries from this voltage cutoff, so I don't have to worry about the short circuit at all. And then make sure we got the right polarity. We got positive there. All we gotta do is stick it in where we got the opening, which is up by the screw for this particular one. And all we have to do is screw it down. And I try to angle it so that it's facing away from the other input, and that's really it. Just righty-tighty, turn it to the right to tighten it, and then when we loosen it, we just turn it to the left. And again, do the same thing with that one. Pretty straightforward, and that's all the wiring I need to do for this particular project. So now, all these resistors are going to do is pass current and get hot. Right now you can see that the board down here, you can tell where it is by where my finger is. It's not as warm as my finger anymore, but it's warmer than the stuff around it. So let's plug in the battery pack to the voltage shutoff, low voltage shutoff module, and there you can see that it turned on. So now we are passing a lot of current, and the display looks a lot better in person than it does on camera, but there you can see that the resistors are heating up. They're getting warmer than the area around there. Also, especially the relay, well there's a hot spot there. There's some transistors or something I think there. But also in the on position, the relay, which is right there, will heat up too. But in any case, it takes I think about 0.7 amps of current, 700 milliamps of current to, not 700, 70 milliamps, 0.07 amps of current for the relay to stay on. And you can see that the resistors are pretty warm. So that voltage, I think it's just because the batteries, they really don't like being up towards the 4 volt range as much as down into the high 3 volt ranges. So I think while it's powering the load, it's going to kind of drop the voltage. But in any case, that's all the resistors are doing, are passing current and basically discharging the batteries to create heat. That's really all that we are doing. So now, I don't want to go all the way to 12 volts yet. So let's hold down this button and let's hold it down. Go to 12 and then raise it up. Let's go up to 14. And we'll come back to this circuit when it shuts off at 14 volts. So now actually this would be a good time to talk about voltage sag. So right now you see 15.2 volts. That's because we're powering the load, and we can measure the batteries directly. So let's see where the wires connect. So one's up there, one's over there, and this one's the negative ones. They're springs. I know it's hard to see, but I'm keeping the light low so we can see the display. And there we go. When I connect to those two sides of the battery, get a good connection, you can see it's 15.6 volts. So slightly less is showing up on there. Now let's remove that jumper. Now we're not powering the load anymore. You can see it's 15.8. Let's see if I can get the battery quick. There we go, the battery pack. You can see we got a higher voltage right now, and it's slowly going up. So the batteries are kind of building their voltage back up. They drop down while there's a load applied, and then they kind of slowly go up a little bit when there's no load. So you'll see a higher voltage when there's no load attached to it than when there is a load attached to it, especially a higher current load. Very small loads, you'll still get an accurate reading. But in any case, that's something to be aware of. Pay attention to what the voltage is while it's under load, not while it's just sitting there not doing anything. And in the last scene, trying to fit everything onto camera, I ended up having this right next to the board. That was not a good thing. We got some bare metal there. We should keep it spaced. So that was mostly a mistake I made from cramping this in too much. But if you do any projects like that, make sure you keep all metal parts away from each other so you don't get any short circuits. So now we have been discharging this for about 40 minutes, maybe 50 minutes even, and we're at 14.6 volts. So it's a really slow process, and I figure, well, we're at this point, while it's under load, we could take a look at the voltages of the batteries, independently. So we got 3.72 volts. That's for a battery number 4, which is our weakest battery. And so we're going weakest to strongest. And this one's 3.78, so higher than that one, which we expect. And 3.79, so tad bit better than that one, which we expect, and we expect a tad bit better with this one too. 3.79, I have the probes backwards, so we have a negative voltage, but that doesn't hurt anything. Just be aware that if you got a negative voltage, you have the probes backwards unless you're expecting a negative voltage. Alright, so now we're a tiny bit past half an hour, past that last clip I did. We got 14.2 volts. Let's take some quick voltage measurements, see where we're at. And we got a little less than 3.6 there, so 3.58. Looks like it's holding steady there. It's a little tricky finding the spot where the battery is. So a little bit higher, we expect that for this one. 3.66. 3.67. And our best capacity battery, 3.67. So they're holding pretty equally for up here, and the one with the lowest capacity is drooping a little bit more than the rest. So we're at 14.1 volts. By the way, I dropped the voltage down to 13.5, and that's where it'll turn off. It won't turn back on until it goes up 3 volts from that, so 16.5. But let's drop this down again. So I didn't think I'd be paying this much attention to the circuit, but making this video is taking a lot longer than I thought. So let's get closer to 13 and pick up from there. Alright, so actually I caught this before it turned off, but that scene didn't go too well. So what happened was we got down to 12.4 volts, and that's where I had it shut off. I set this so that it won't turn back on until we go 2.5 volts above that 12.4 volts. So let's lower that now. Where are we at? 13.6. So if we hold this and lower it down to 1 volt, and then wait for it to kick in. Let's take a voltage reading of the weakest battery right now. And you'll see it's 2.78, but it's quickly dropping. And when the total voltage, so we're almost 2.5 volts right now. And, oops, lost my connection there. And we did get to 2.5 volts. So this is too low right now. We just proved that. We need to raise this. Let's hold this up to 13 volts. So for this particular battery pack, I would not let this drop below 13 volts. So it was just briefly at about 2.5 volts and rose back up. So I think we'll be okay. But that's one reason why I'm using these cheap batteries to do this first test. And so it really rapidly, it only took about 20 minutes to go from the last scene that I did before this one. The voltage was rapidly dropping when I tried to film the scene for the first time, and so when we left off, what was it, like 14 volts, a little bit more than 14 volts, that was pretty much the last of our useful power. We had a little bit more, but that was really it. So that's the way these batteries go. They don't like to stay up by 4.2 volts. In fact, they self-discharge for a bit. They kind of rush when you start using them to 3.9 volts, in that range, and then they have a lot of power from like 3.9 volts to I think about 3.3 volts or so, something like that, and then they start going down quickly from there. So you want to kind of stay a little more in that medium range. You know, you don't need to go to the extremes. In fact, it's not good for the batteries to go to the extreme. You want to leave a little space. But these other batteries, they still have quite a bit of charge. So we got 3.4 with no load though on all of them. And let's unplug it and plug it back in and see how they do with the load, because it'll snap back on until we get to the cutoff, and it already cut off. So yeah, this battery I think is pretty much done. It's given all that it can give. It's the weak link. But anyways, hopefully you learned a lot from this. This is a really long video. I didn't intend for it to be this long, but anybody that stuck around this long, thanks for sticking around, and see you in the next one.